This is kind of an important review question right here. Camille, do you remember the answer to this one? Camille, are you there?
Oh, I'm here.
Do you remember the answer to this question here?
Yes. Isn't it in the Kelvin?
That's right. That's right. Kelvin is the only one that needs to always be Kelvin. And that's because all these other parameters, atmospheres, it can go from 0, which is the beginning point, linearly upward, right? It can go from 0 linearly upward. Volume can start at 0 and go linearly upward, right? Kelvin can do that. Celsius doesn't do that, right? Celsius goes through 0 and then goes into negative, right? And so it's not a linear relationship starting at 0 and going forward, right? So all of these parameters that we've been talking about, pressure, temperature, volume, the moles of gas N, that can go from 0 to infinite, right? All of these parameters start from 0 and can get larger. But degrees Celsius doesn't, but Kelvin does. So we have to make sure we use Kelvin. Okay. And then we talked about how we can remember our gas law relationships. How do we remind ourselves of what the gas law relationships are? And I'll kind of do it for you here, and hopefully you can gather some way of your own, which is similar to this, to kind of think about and remember what these relationships, the characteristics of these different gas, what the relationship is between these different characteristics. Okay, so the different properties are, the pressure, the temperature, the volume. All right, temperature, pressure, and volume of a given gaseous situation. And what do you think, Harry? How do temperature and pressure go together? Do they increase directly or indirectly? What do you think, Harry?
Directly.
Directly? So you're saying if I increase the temperature, that will increase the pressure? Okay, so we can kind of draw a vessel and think about that. When we talk about this process, what is it we have to keep constant, Harry? If we're changing the pressure, well, I want to make sure you guys recognize that when we talk about identifying the relationships between two of the parameters, the other one, volume, or maybe even N, meaning moles of gas, the other ones have to remain constant, right? If we made changes in 3 of these, then how would the 4th one change? It could change up or down depending on the kinds of changes. So whenever we think about how pressure and temperature relate to each other, for example, the other parameters that we're not mentioning have to be fixed, right? Okay, so we're saying that if we increase temperature on a condition, the pressure will increase. So here's our initial condition, low temperature, right? And then we're raising the temperature. We'll just say high temperature. Okay, now I can represent the temperature of these dots. How do I represent the temperature of the dots? Do you remember, Harry?
They'll be moving around a lot more?
Yes, at high temperature they will be. And I can represent that by the length of my little vectors here, right? So I draw vectors on here of the gas molecules moving around, and then I draw them moving around with larger arrows indicating that they have a higher temperature, right? Now, at a higher temperature, more movement, more collisions, we would expect that to indicate that the pressure has increased. Very good. So as temperature increases, pressure increases. So there's a direct proportionality there. All right. Now, if I want to write an equation, how do I write it, Precious? how do I write my equation if I want to express pressure and temperature? Let's start off with a pressure here of 1 atmosphere. And we said that the pressure goes up to maybe 5 atmospheres. Okay. If our pressure went up, or if our temperature went up fivefold, if our pressure somehow increased fivefold, that means the temperature also increased fivefold. So maybe if we go 10 Kelvin to 50 Kelvin, all right, Precious. So now we need to try to think what kind of a relationship with our pressure 1 and our temperature 1 will fit with our pressure 2, temperature 2.
Would it be like P1 T1 is equal to P2 T2?
P1 T1 what'd you say? P1 T1
Yeah.
equal to
Is
P2
P2?
T2?
Yeah.
All right. So that's perfect. We write that down, and we don't know if it's right or not yet, but now we can put our numbers in. Let's put our numbers in and see if that's right. Does that fit, Precious?
Like 1 multiplied by 10 is equal to, oh wait,
It doesn't work, does it?
yeah.
Okay, good. So it's not that way. So what is the other way it could be?
Oh, it's like P1 over T1
Uh-huh.
is equal to P2 over T2.
Okay, does that fit with our numbers?
Yes.
It does. 1 over 10, that's 1/10. 5 over 50, that's 1/10 as well. Very good. So we have regurgitated in our minds this relationship between pressure and temperature, just kind of thinking about our experiences, drawing little pictures, that sort of thing. Okay? Now, we want to include volume in here. Include volume in here. We can do it separately. Who's up? Sarah? We can do this separately. We can say, all right, how do pressure and volume relate to each other? So that means that temperature and moles are going to be kept constant, right? But if we have the volume able to change and the pressure able to change, right? What does that mean? The volume is going to have to be like a balloon, right, Sarah?
Right.
Something that can change like that. What do you think? If I increase the pressure, how is that going to influence the volume?
The volume will decrease.
The volume will decrease on the balloon. Yeah, so here's a balloon, right? And if I increase the pressure around the balloon, right? And we said that, that's like taking the balloon underwater or something, then the volume of the balloon will decrease. Okay, so they're inversely proportional, right? And so what kind of a relationship, if I had an initial pressure here, or initial volume, let's choose a volume of maybe 2 liters. And this volume here is now 1 liter. Okay. Our pressure initial, give me an example of initial pressures, Sarah.
Do 1 atm.
All right, 1 atmosphere. And then what would the pressure here be?
That would be 2 atmospheres?
Yeah. We know that if you double the pressure, the volume will be cut in half. So 2 atmospheres, right? And now we want to kind of formulate an equation. What is our relationship between P1 V1 and, P2 V2 here? Can you see it, Sarah?
Yeah, P1 V1 equals P2 V2.
All right. Very good. Now this, in conjunction with P1 T1 equals P2 over T2, like that, right? We can combine these together and say that in a scenario where we knew all three parameters, P1 V1 over T1 would equal P2 V2 over T2. All right? So we have what's called the combined gas law, and we just kind of, hopefully you can see how we derived that ourselves. We remembered that ourselves. Now, you know, how do we know this stuff? How are we coming up with this stuff? You have to draw on just some experiences. You have to draw on a realization, for example, that if I took a balloon and dragged it underwater, it would shrink. I don't know if you've had that experience or not. Maybe you've bought some balloons at a fair or something and then driven up to the mountains, the balloons expand, right? That's one way of recognizing that as you go up high in the mountains, the pressure decreases. Brielle, why is it that up in the mountains there's less pressure? What does that mean when we say there's less pressure up in the mountains? What's going on, Brielle?
I'm not sure, but I know that the higher you go up, like you were saying in the example where the higher you go to space, the less pressure there is on you, and the deeper you go in the ocean, there's more pressure. So there's just less moles of gas the higher you go up.
That's right. That's right. There's less moles of gas, and that's another relationship that we didn't really emphasize too much, but if you increase the moles of gas, you increase the pressure, right? Because there's just more stuff there to hit you, right? So in this vicinity of the environment, there's a certain number of moles of gas, right? Those moles are bombarding the outside of your balloon that's in your car or whatever it is that you're monitoring pressure with. And as you get towards the top, the molecules, the number of moles of stuff just decreases, right? So there's more down here, but it just gets thinner towards the top, right? So there's just less of it. There's just less of it. Okay, very good. Now let's get back to here, make sure there's nothing else we need to kind of review here. Yeah, I think that's it. So now we're going to get into